Okay, so we've analyzed how strong acid and strong base solutions behave and what ions appear and disappear in those. Can we do it with a weak acid? Yep. Here we have methanoic acid, also known as formic acid. And that can react with water. And this hydrogen pops off, so we get the methanoate or formate ion. And instead of H2O, we get H3O. The ability to make this is why we call it an acid. And we started with 0.100 moles per liter of HCOOH, and they say 4.2% of it, roughly 4% of it, dissociates. So, of this 0.100 that used to be there, 4 goes away and we're going to be left with 0.96. I'm pretending this is 4, that's going to be close enough for most purposes. You can make this 0.958 if you want to really nail it, but I think this will be good enough for us. So 4% of these ions dissociate. What happened to them? They turned into methanoate ions. We're going to have 0.004 of them, and the same amount of H3O. So those will be our concentrations of the two products. Notice we never work out the concentration of H2O because it's the solvent. The concentration of this is probably like 55 moles per liter or so, and it isn't significantly affected by the tiny little bits of acid that are moving around in it. It's like analyzing a population of fish. You don't keep track of how much ocean water there is. There's an overwhelming amount. Don't worry about it. The things that really interest us are the acid and the dissociated pieces of acid. So, if this solution is ionized like that, what's present in the highest concentration? Undissolved acid. Every time we talk about a weak acid, it means most of it does not dissociate. So we put in 100 units of this, only 4 of them actually did anything. The other 96 are still floating around doing nothing. They didn't break up. They didn't contribute any hydrogen. They're just kind of useless. Will the next question be a weak base? No, it's another weak acid. Okay. 0.2 moles of the imaginary weak acid is dissolved in 1 liter of water. Okay, what are they doing here? Okay, we have this acid HW. Let's predict what that's going to do. HW should react with water like everything does in this chapter. It's an acid, so it'll give away a hydrogen with the conjugate base, and H2O will turn into H3O upon picking up that hydrogen. Easy enough. The HW concentration would be number of moles divided by volume, so 0.2 moles divided by 1 liter is 0.200 for our initial concentration. And then some stuff happens, and we end up with an OH concentration of 1 times 10 to the minus 9. Why would we care about that? Well, we don't care about that because it's not any of our products, so it's not directly useful to us. But if you know the OH concentration, you also know the H3O. H3O concentration is always the ion product for water divided by the OH. So we can do 1 times 10 to the minus 14 divided by 1 times 10 to the negative 9. And we get our H3O concentration is 1 times 10 to the minus 5. You can write it that way, or you can write 0.00001 moles per liter if you wish. If this is our H3O amount, these are always equal, or assuming there was none to begin with, these have to end up equal because they're being produced in equal amounts. So both of those concentrations must be 0.00001 moles per liter. And how are we doing? Do we have the stuff they want? They wanted H3O concentration. Here it is. It's either 0.00001 or 1 times 10 to the negative 5 moles per liter. W concentration, same amount. These are one-to-ones. Like if you, every time you produce an empty bottle, you also produce a bottle cap. There's always one cap for per bottle, so their amounts have to end up the same. And how much of this remains? Well, we started with 0.200, and then this much dissociated. So 0.2 minus this little amount, 0.00001, gives us, there's hardly any difference, 0.19999 moles per liter. Now, you could maybe try to take that literally, but really, looking at these numbers up here, our concentration only had 3 significant digits, and so this afterwards really should only have 3 significant digits or 3 decimal places, meaning we only get to keep up to there, and then we round up. So really, the honest answer here is 0.200 moles per liter again. It might bug you to say that this number hasn't dropped when we know it has a little bit, but the honest truth is this difference is so small that it's not detectable to this level of precision. So this really is the right way to say it. It's saying, look, there was a small decrease, but it's not enough to warrant me going to 199. It's a smaller difference than that. Hope that's acceptable or at least tolerable. See you next time.